This is our assignment to get more practice with slope fields. So if we look at the first page here, we're going to make some slope fields on our dot paper. Our first problem has only x's in our formula for the derivative, so we know that once we find the value for an x coordinate, we can fill in that same slope all the way up and down the column. So for example, when x is 0, do you see that the slope will be 1? So we can go all the way up and down, filling in slopes of 1. When x is equal to 1, the slope would be 2. So once you make one of these slopes, fill in more quickly. And at 2, we have a slope of 3, so these are getting steeper. And when x is 4, we have a slope of 5. So I'm not being exceptionally careful. At -1 for x, do you see that that's where our slopes will be 0? At -2, we'll have slopes of -1. And at -3, we'll have slopes of -2. All right, in question number 2, we only have y's in our formula for the derivative. So remember the term, this is an autonomous. If I don't get carried away here with spelling, an autonomous differential equation. So this time when y is equal to 0, for example, our slope will be 0. So we will have an equilibrium solution. So remember that when you get a horizontal line as a solution curve, that's an equilibrium solution or a constant solution. When y is equal to 1, we'll have a slope of 2. So we can go all the way across quite quickly. When y is equal to 2, we'll have slopes of 4, so they get very vertical here. And likewise, on the negative side, when y is -1, we'll have slopes of -2. So I want to make sure we're kind of pointing towards a target point when you make the first one, and then just quickly make the rest of them parallel. And then at -2, we'll have our slopes of -4. All right. In number 3, our formula for the derivative is x plus y. So look for some patterns. When y is equal to -x, then dy dx will be equal to 0. So along our 135-degree line, that's where we'll get slopes of 0. So along this diagonal. And you could think then what's going to happen at some other patterns here. When y is equal to 0, then our slope is just equal to the x coordinate. So when y is equal to 0, so here we'll have x is equal to 1 will determine our slope. X is equal to 2, x is equal to 3, -1, -2, -3. And likewise, when x is 0, when x is equal to 0, our slope will just be equal to the y coordinate. So here we'll have a slope of 1, a slope of 2, a slope of -1, -2, and so on. And then we can start filling in and looking for some other patterns here. So at 1, 1, we've got a slope of 2. And at 1, 2, we've got a slope of 3. And at 2, 1, we've got a slope of 3. And at 3, 0, we've got a slope of 3. So can you see that the diagonals might be another hint for going a little quicker here. So at 3, -1, we've got a slope of -2. And at -1, -1, so again, we can go down these patterns of the diagonals and finish filling in our slopes. At -2, 1, we've got a slope of -1. I'm sorry, that's the slope. Let me try that again. My arithmetic, that's -1, +3. So that would be a slope of 2. All right, so we can finish filling in here our slope field. Doing the arithmetic along the way. So that diagonal pattern, I think, is the most helpful in this problem. And I'm missing a point here along that diagonal. All right, and here we are back to having a derivative with only x in it. So when x is 0, we will get our horizontal. When x is 1, we've got slopes of 2. So we start seeing these patterns repeating. And when x is 2, we've got slopes of 4. And at 3, we've got slopes of 6, even more vertical. At -1, we've got slopes of -2. So can you see how we're going to have the opposites across the way here? At -2, we'll have slopes of -4. And then -6. All right, in question 5, we're back to another autonomous differential equation. And this will have a constant solution, so notice when y is equal to 1, then dy dx is equal to 0. So when y is equal to 1, there's our equilibrium or constant solution. You always want to look carefully for those. That will be important in any application of this differential equation. When y is equal to 0, we'll have slopes of -1. When y is equal to -1, we'll have slopes of -2. And at -2, we'll have slopes of -3. And at +2, we'll have slopes of +1. I better make those a little more angled. And in number 6, we've got the opposite of the ratio of y to x. So some important things to notice here. X cannot be equal to 0, so make sure that you have no slopes, no tangent lines on the y-axis. X cannot be equal to 0. And we have an equilibrium solution when y is equal to 0, then dy dx is equal to 0. So we'll have slopes of 0 here, but stay off the origin. The origin is forbidden here. And then we could say when y is equal to -x, then we'll have slopes of +1. So when y is equal to -x, oops, and I missed that. That would be at 1, 1. There's our 135-degree line. And what about when y is equal to +x? Then we'll have slopes of -1. So on this diagonal, slopes of -1. And then we can start filling in some more points here. So at the point -1 for x, +2 for y, we'll get a slope of +2. So I'll leave it to you to start doing the remaining arithmetic here and try to be as accurate as you can drawing your slopes. Here they should be getting more and more horizontal as we go through. Let me again try to show a pattern here. This was 1, so we want to get less sloped here and more here. All right, so let's see if we do some matching with these. So as you look through here, we've got 2 derivatives that have only x in them. So these are the 2 where the columns should be consistent. So we could start using process of elimination. So if you look, for example, at A, if you go down a column, you can definitely see the slopes are not all equal. So we could definitely rule out A without even much thinking about it. So the ones where the vertical columns match up appear to be B and C. So as long as we're talking about that, let's continue here. If our derivative is equal to the sine of x, so I think we all know that one of the solutions, if you reverse the derivative here, we know that a solution curve would be negative cosine of x. So can you see just by looking at the slopes which one a negative cosine graph might fit in? Do you see here that you could fit a negative cosine graph into this one, where you would not be able to do that in B? Some other things that you might look at for number 10, when the slope is just equal to x, obviously on the positive side we have to have positive slopes, and on the negative side we have to have negative slopes, and that's not happening in letter C. So some very quick process of elimination here. I think we can figure these out. Notice that 9 depends only on y's, so 9 is our autonomous differential equation here, so we know that the row has to be consistent. So we've used A and B. Whoops, try that again. I think I should have said C there. So if we look across the row here in A, this one is autonomous, but in D it is not autonomous. So again, you can do more than this to double check, but trying to get through here quickly. So if we checked one of these out for 9, if, for example, we put 2 in for y, do you see that that should be our solution? That should be our equilibrium solution that produces derivatives of 0. So we're pretty clear here. I hope that 9 would be A. And of course that leaves 8 as D, but let's double check here. Do you notice that this has y equals x line, appears to have derivatives of 0? And look at your formula. Is that true, that when x and y are equal, you would get slopes of 0? So do a little bit more than just a single check here so that you're sure that you haven't mismatched any of these. In question 11, we might do the same thing here. Look for the simple ones first. Here's one that depends only on x, so our vertical columns have to be consistent. And in 12, here's our autonomous, depends only on y, so our rows have to be consistent. So as we look through our choices, as we look vertically, it looks like B is the only one that has vertical columns being consistent, and C is the only one that has horizontal rows being consistent. We might do another check here. Notice in C that when y is equal to 0, we get an equilibrium or a constant solution. And that is exactly what we would expect for number 12. So let's put C here for 12. And let's check out B a little bit more closely. You might notice here that it looks like when x is some positive number, depending on how we're counting here, that this is where we get our 0 slopes. So when x is equal to 2, look at what should happen in the formula for number 11. When x is equal to 2, should we have dy dx equal to 0? And that definitely works as we expected it to work. So, sorry, let me get that out of there. So as we thought, we could do some process of elimination. We've seen some of these before. Here we know that y cannot be equal to 0 for 13, so there should be no tangent lines on the x-axis. And when y is equal to negative x, then we can see that our slopes should be positive 1. And that appears to be true in D. And in 14, x and y, when y is equal to negative x, then we should get slopes of 0. dy dx should be equal to 0 on that diagonal. So if we looked at that diagonal, that would be a good way to compare. For one of them, on the 135-degree line, we should have slopes of 1. And for the other, we should have slopes of 0. So I think that would be enough for us to put A for this one, and that is D for this one. And you could try a couple more points. You could see what happens here as we go through. All right, let's press on so we don't get too long here. We've got a lot of problems to go yet. The slope field is given for these solution curves. So which one? Well, we could do this a couple different ways. We could find the derivatives of these. These are all simple equations. So c dy dx would be equal to the opposite of e to the x. dy dx would be negative sine x. And here dy dx would be equal to 1 over x, so we could certainly work that way. Or we could look at the slope field and say, well, which one of these equations could we fit into this equation? So if we chose a point, do you see that we come up with slightly rising curves here? Do you see that none of the rest of these? Can you fit a parabola in here? A parabola doesn't fit on that slope field. And e to the x curve likewise doesn't fit. And e to the negative x curve would look like this, and that certainly doesn't match the slope field. A cosine wave, can you see putting a cosine curve in here as a solution curve? So a couple different ways of doing that, but which solution curve fits the slope field is probably the most obvious. All right, in 16, again, we're given a slope field. Which of these could be a specific solution? So I think we can see here what appears to be happening if you choose a point here to see. It looks like, to me, this looks like it would be a cubic graph. It definitely gets very vertical here and very vertical here. So it's growing quickly, so it certainly doesn't fit sine and cosine waves. What happens in this quadrant certainly doesn't match a parabola. A natural log of x would have to have no slopes from 0 to the negative, so I think our instinct of what looks like the curve that fits there is exactly enough to answer that question. All right, a couple that might look like free response questions. So here we're given a differential equation, the product of xy divided by 2. So we have to make a slope field here. So notice that when x is equal to 0 or y is equal to 0, dy dx will be equal to 0. So we can start filling this in very quickly. So on each axis, we'd have 0 slopes. And then think what happens here. If x and y are both 1, we would get a slope of 1/2. And likewise, if they were both negative 1s, we would get the same slope. What if they were positive 1 and negative 1? Then we would get slopes of negative 1/2. So we can start filling this in fairly quickly. If we did the point 2, 1, we will get a slope of 1. And likewise, down here we would get a slope of negative 1. And if we did the point negative 2, 1, so we would get a slope of negative 1. And down here a slope of positive 1. And how about the point 3, 1? Then we would get a slope of 3/2, so up 3 and over 2. And then we figured out here that we have opposites of these. So that's a little bit bigger than the previous one. And how about the point 1, 2? That would still be a slope of 1. And the point negative 1, 2 would be a slope of negative 1. And at 2, 2, we would get a slope of 2. So over here we would have a slope of negative 2. And at 3, 2, 6, if x is 3 and y is 2, we would have 6 over 2 is 3. All right, so not too much effort there to fill that in. Part B. In B, we're looking for the tangent line through the point 1, 1. So we need to find the slope dy dx at the point 1, 1. So we would have 1 times 1 over 2. So our tangent line by the point slope formula. And then we're asked to use that equation of the tangent to approximate the value of the curve at the point 1, 2. So let's put 1, 2 into our equation. And I guess I'm reading that wrong. That doesn't say 1, 2. That says find f of, use our tangent line to estimate f of 1.2. All right, sorry. Let me plug 1.2 in for our x and find out what our y is. That makes a little bit more sense. All right. So we would have, this would give us a 0.1 on the right side, so we'll add the 1. So we believe the point 1.2, 1.1 is our estimate. All right, now let's see. In part C, find a particular solution to the differential equation with that initial condition. All right, so in part C, we're going to take our differential equation and separate variables. So by separation of variables, let me right away write in what our initial value. Our initial value is going to be the initial condition of 1, 1. That's maybe what I was reading a minute ago. And then we're going to find f of 1.2. So we're going to compare this similar to part B. All right, but now we're going to separate variables. So I'm going to divide both sides by y and multiply both sides by dx and then integrate. So I hope this goes quickly here. Raise the exponent to 2 and divide by it, and add a constant to both sides, which we'll group together on the right side. And then we can either substitute our initial value in now, or we can substitute it in later. That would really be your choice. It's not difficult to plug it in now, since we know the natural log of 1. If we put it in now, the natural log of 1 we know is 0. So we could at this point find out that c is negative 1/4. Or you could do that at some point later. Let's see what would have happened if we would have proceeded here. We would exponentiate both sides, and of course you don't have to write this. You know that this is going to be equal to y on this side. And on this side, I hope that you now remember that when we have this sum in our exponent, the sum can be split up. So this exponential process, I hope that you can proceed quickly. And now again, you could substitute your 1, 1 in at this point, and you would get the same answer here. So if we put 1 in, here we'll find out that c is 1 over e to the 1/4 or e to the negative 1/4. And it's going to turn out the same way in this process. If we already found that constant, 1/4 x squared minus 1/4. So either way, now we're going to come up with e to this exponent, 1/4 x squared minus 1/4 is equal to y, and we can have a plus or a minus in there. So this e to the negative 1/4 we could write as a constant. So Lots of different ways of writing this solution in either case. You might factor that 1/4 out there. So some equivalent form, depending on how you solved this. And then we're asked to find out what is f of 1.2 if we did this equation. So if we put 1.2 squared here and grab a calculator, we'll come up with 1.116 as our approximation. All right, and then we are asked to compare our answers. So I'm not exactly sure. I think my slope field, I think I covered up part of the question in D, but they're asking us to compare our two answers. So 1.116 compared to our estimate was 1.1. So I don't know if they want to find a percentage of error or just compare those two. So I covered up that question, so I'm going to continue. And then in part E, your estimate in B, was it an underestimate or an overestimate? Well, let's look at our slope field. Can you see that at that point we were using of 1, 1, can you see that our solution curve, you see that our solution curve is concave up. So since the slope field shows that solution curves are concave up at 1, 1, our tangent line approximation is an underestimate. And indeed it turned out that it was. 1.1 is smaller than that answer that we came up with of 1.116. All right, let's proceed here. And one more, our differential equation, and we've done this before, this problem. So I'm going to pause the video. Again, what do you know here? We know that y cannot be equal to 0. We know that x equals to 0 gives a constant solution or an equilibrium solution, because that would make all of the slopes equal to 0. We know that on the line y equals x, that the derivatives are all equal to 1, and y equals negative x. The derivatives were all equal to negative 1. So we've done this before. It looked like kind of the hyperbolic solution. So I'm going to pause the video here while I draw these in. All right, and now I'm going to move on to part B, our solution curve through the point 0, 1. So we came up with this hyperbola type curve. And then in part C, find the particular solution that goes through 0, 1. So our point 0, 1, we can tell here what should happen, but we're asked to actually solve our differential equation. So let's remember that we want the point 0, 1 here as our initial condition. And let's separate our variables. So we'll move the y with the dy, and we'll integrate. So we'll have 1/2 of y squared, 1/2 of x squared, plus our constant. If we double both sides right away, so we'll change that to a constant 2. And then remember that we'll have this plus or minus the square root. So this is one of those questions where you know what you want by looking at the y coordinate here. You might want to do your substitution first to find out what c is. That's really up to you. If we put 0 in here and 1, so we can see that our constant is 1. And then we'll have plus or minus But remember that if this is on our solution curve, that tells us that we only want the positive branch. So through the point 0, 1, we only want the positive branch of this graph. And then in part C, or in part D rather, we're asked to sketch the curve through 0, negative 1. So we would have this branch of the curve. And then for part E, that solution through 0, negative 1, we would have our same solution. So we would get to that same point of y squared is equal to x squared plus c, and we would put negative 1 in, and you can see that we're still going to have the same value of c, of positive 1. But here we're going to keep only the negative branch of the curve. So that's the negative branch of the hyperbola. All right, and very quickly I'm going to add on an extra point here of what happens when we have this no differential here. There's no values of dy dx here. So what about a solution if I added a question f here? What about a solution curve that goes through negative 1, negative 1? What would it look like? Well, at negative 1, negative 1, we would have this line here, and then you would put an open circle and stop right there. So stop with an open endpoint. So I didn't yet choose one that works that way. And what if we were doing our solution that way? What if we were solving our differential equation? So if we got to our y squared equals x squared plus c, and we put negative 1 in there, we can see that what would happen if we're putting negative 1 in as our initial point, c would turn out to be 0. So y squared is equal to x squared, and y would be equal to plus or minus x. And then how would you choose that? You would know that because of our initial point, we would keep y is equal to negative x, but now you would have to add a domain because you are not doing the entire line here. You are only doing this for the domain of x less than 0. So there's an extra bonus part of the problem that could be very important later on.